Well, hello everyone. I'm Konstantinos and I will present SIRD, which is a protocol that tackles data center congestion using a receiver-driven approach that is sender-informed, which is the point of the talk. So let's first establish why we're talking about congestion control in data centers. One reason is that it directly affects application performance. And the reason for that is that it has a very core mission, which is to decide if it's safe to send a packet to a server. So if it's very conservative in this mission, it will hurt the performance of throughput-intensive applications like disaggregated storage. And if it's too aggressive in this mission, it will inevitably form queuing in the network, and that will degrade the performance of latency-sensitive applications, like, for example, USENIX, where you can get an order of magnitude more latency due to queuing, and maybe 2 orders of magnitude if you have packet loss. The other reason we talk about data center congestion control is that the data center environment itself is changing rapidly. So right now, link speeds are pushing 800 gigabits, and switch buffers are not keeping up with this. So now it takes less than 2 milliseconds to fill the whole capacity of a modern switch at 800 gigabits. So overall, we talk about congestion control because it affects application performance, and at the same time, the environment in which it operates is evolving very quickly. But what does it mean for a data center network to be congested? Well, here is a data center network with servers at the bottom row connected with switches and links, with the most common and most severe form of congestion being incast, when multiple flows converge to the same receiver. But also congestion can happen at the core of the network when multiple flows, due mostly to flow collisions or oversubscription. And finally, congestion can happen at sender uplinks, when a single sender sends to multiple receivers. And in this case, it's usually considered less severe because the queues themselves form inside the servers where there is more capacity. And of course, there have been many proposals to improve congestion control in data centers. And they can be broadly classified into 2 categories, sender-driven and receiver-driven. And I'll make a brief mention of the 2. So sender-driven approaches are reactive in nature. It's the try and back off approach. So the sender sends, and if something goes wrong, then it gets a feedback and then slows down. And this feedback is usually some form of congestion feedback, say delay or ECN. And many improvements have come from using richer congestion signals, like, for example, in-band telemetry. But this increases the dependency on switch features, which then increases operational complexity. But this approach is naturally good at handling congestion wherever it happens in the network. But the downside is that it takes some time to converge, and this time queuing can form. The other approach is receiver-driven schemes, where the idea is proactive. It's basically admission control. A receiver is allowing the sender to send by sending credit packets to the sender. And many of these approaches also use switch support to maximize performance. But overall, this approach is ideal for incast because it can avoid congestion altogether there due to admission control. But doing crediting solely based on the receiver's view, as we will also see later, leads to either low throughput or high queuing. So to recap, we observe that the existing approaches sacrifice at least one of either throughput or queuing, or generality in terms of managing congestion everywhere, or operational complexity in terms of, let's say, simplicity or dependence on switch features. So given these limitations, ideally we would like to have a congestion control protocol that deals with incast, which is the worst case of congestion, through receiver-driven admission control, but also addresses congestion everywhere, no matter where it happens, and then achieves high utilization, so high bandwidth utilization with minimal queuing, while also minimizing the dependence on switch features, like, for example, priorities. And we argue that to do this, we follow a simple approach to get this, which is that single owner links, so congestion on single owner links, in this case, switch to receiver links, should be managed proactively through receiver-driven admission control. But congestion on shared links, that is, links that are shared by multiple senders at the same time, should be managed reactively. using congestion feedback from senders and the core to do credit allocation as a function of congestion. And we will see that this approach enables enables the receivers to do precise credit allocation, which yields high throughput with minimal queuing. So let's build SIRD together, one bottleneck at a time, starting from the most straightforward one, which is the incast case. So we'll do this through an example, where in this case we have two senders on the left, a switch in the middle, and a receiver on the right. And in SIRD, we give each receiver a limited amount of credit, which we call B, and B is for budget. This is the amount of credit the receiver can distribute to senders. So if a sender wants to send to our receiver, the receiver will issue credit, and then the sender will use it to send back data. And notice that in this case, the receiver used all of its credit, meaning that it effectively used the equivalent of one bandwidth delay product, or one BDP of credit, to pull one BDP worth of data. Notice BDP, we will use it a lot. And then if another sender wants to send, then the receiver can easily split its credit between the two without any convergence time and enforce a policy or whatnot. So in this case, we see that this approach can deal with incast without any queuing at all. In fact, in this specific scenario, queuing is impossible because the receiver doesn't have enough credit to pull enough data to cause queuing. So this is done. Let's now do the tricky part, or the more interesting part, which is how to handle congestion at the sender uplink. So we'll do this. Before we see how, let's see what the problem is if we take the current approach and naively adapt it to an example where we have a congested sender. So in this case, we have a sender on the left, a switch in the middle, and 4 receivers on the right. Again, each receiver has 1 BDP worth of credit to distribute. And we start by S1 sending to the second receiver. Everything is normal. The receiver is giving away all of its credit. And then the same sender wants to send to everyone, becoming effectively congested. Now, because each receiver is not aware of the overall situation, it gives away all of its credit to greedily try to maximize its own throughput. And of course, this credit cannot be used by sender S1 because it's bottlenecked at the uplink. So this credit ends up accumulating at S1, which becomes a problem if another sender appears and wants to send to one of the receivers. Now we have a mismatch. So if we step back a little bit, the problem here is that receivers don't really know how much credit they should allocate to S1. And so what they end up doing is they overallocate, which yields throughput loss effectively at the end. So the problem of congested senders is not new for receiver-driven schemes. There have been proposals like creating a bipartite match between senders and receivers before sending, or programming switches to do hop-by-hop credit management. But we will focus on the approach called controlled overcommitment, which was introduced by HOMA, and it's a simple one. It's the idea that each receiver should get a lot more than 1 BDP of credit to distribute to senders. This way, even if senders accumulate credit, the receiver has a bunch more to give out and get throughput. The problem with this is that it leads to queuing. So let me illustrate this. So here we see what happens if there is no overcommitment. So each receiver has 1 BDP, and this leads to up to 1 BDP of data in flight. But if we give each receiver n times BDP worth of credit, we end up with, again, up to 1 BDP in flight that does useful work, and then n minus 1 times BDP that is queued. So the question is it necessary to overcommit like this and face high queuing? And we say that it's not, as long as credit does not get stuck at senders. And SIRD does something very simple. It reactively limits the amount of credit that's accumulating. Effectively, if a lot of credit accumulates, it pushes it back down. So, and we do this through a threshold. If more than the threshold accumulates, then the sender will inform the receivers, and the receivers will reduce their allocation to the specific sender. Let me show you this to you through the same example as before. The only difference here is that we have a variable that is keeping track of how much credit each receiver is allowed to allocate to sender S1. We start again the same as before. S1 is sending to the second receiver and then wants to send to everyone. But we end up in a situation like this where the receivers still have credit available. And this is because, as I described, the queue has a threshold. Every time the threshold is exceeded, the sender is marking a bit in the header of data packets with a signal we call CSN, congested sender notification. It's like ECN. And then each receiver takes this as input and is running an additive increase, multiplicative decrease algorithm. And then eventually each one of them converges to allocating up to 0.35 times BDP worth of credit to the congested sender. So if we step back a little bit, what's happening here is that each receiver reactively is adjusting to the availability of the bottleneck. And in this way, we can get more throughput with less credit. And in fact, let me show you this through a simulated scenario. Here I'm showing queuing, where lower is better, versus throughput, where higher is better. This is from a 144 host web search simulation at maximum load. So this is worst case in terms of queuing. And I'm showing HOMA, which, as a reminder, this is the protocol that introduced overcommitment. What performance it gets as it scales its level of overcommitment. So when it does not overcommit, it gets relatively low throughput, but at very low queuing. And then if it overcommits by 7 times, it gets high throughput, but high queuing. Now SIRD, without overcommitment, it gets a bump in terms of its throughput by 20%. And then by overcommitting modestly, we get an order of magnitude less queuing. And at the same time, in this case, the switch SIRD would use less than 10% of the switch's capacity. And note here that SIRD benefits from modest overcommitment, and the main reason for that is that some credit still accumulates at senders by design, since the sender threshold is non-zero. So we covered sender uplinks, receiver downlinks. Let's cover how SIRD handles core congestion. This one is simple because SIRD treats core links the same way it treats sender links, because all of them are shared by receivers. We extend the same control loop we have for senders for the core. And effectively, the ECN feedback propagates from the core to receivers, and then receivers adapt their credit allocation as a function of both sender congestion and core congestion. And of course, they do so based on who is most congested. So to recap, in SIRD, each receiver operates with a modest amount of credit, which by default we set to 1.5 times BDP, and this caps how much data can be scheduled towards that receiver. And then each sender gets up to 1 BDP of that, and then the receiver adjusts the per sender allocation as a function of congestion at senders and at the core. This allows SIRD to get high throughput with minimal credit, which yields minimal queuing. Now, there are other design questions that should be answered, and you can find them in the paper, but for now I'll just address how SIRD reduces message latency. So message latency, there are two steps to reducing message latency, and I'll mostly focus on small messages, which are usually the most latency sensitive. So first of all, in SIRD, we send small messages outright without waiting for credit. That's one part. And the other part is that generally small message latency is caused by network queuing. But as we've seen, SIRD causes minimum queuing. So effectively, SIRD strongly reduces the need for switch priorities to bypass queues, which other protocols have leveraged to great effect. This reduces operational complexity, but of course SIRD can use priorities if they are available, and sees some benefit from that. So we evaluated SIRD in detail using both simulation and a 100 gigabit testbed. And we answer many questions in the paper, and I invite you to check them out. For now, I'll just show you how SIRD compares overall to other baselines. So we use a 144 host topology, and we simulate 3 workloads over 3 different traffic matrices, including one where the core is the bottleneck. And we also use 2 priority lanes in this case for SIRD. This slide shows the normalized comparative performance of SIRD versus the other baselines in terms of goodput, where higher is better, queuing, where lower is better, and 99th percentile slowdown at 50% load, where of course lower is better. And I'm just showing now the performance of SIRD, which, as you can see, simultaneously optimizes for all metrics. And we compared SIRD with 2 sender-driven approaches, DISTCP and Swift, and 3 receiver-driven approaches, ExpressPass, HOMA, and DCPIM. And in the interest of time, I'll focus the comparison to HOMA, which is the closest in terms of philosophy to SIRD. Well, in terms of goodput, SIRD matches HOMA, and then in terms of 99th percentile slowdown, it's second best to HOMA, which is shown to be near optimal in that regard, and then does this with an order of magnitude less queuing in the network. So to conclude, SIRD is a simple idea, is that single owner links should be managed proactively and shared links should be managed reactively, which allows receivers to coordinate. This allows SIRD to handle congestion everywhere and enables high throughput with little credit, which in turn yields little network queuing, and that yields further low network latency for short messages. You can find SIRD, both the implementation and the simulator, on GitHub, and thank you very much for your attention.